So, hello everyone again. This is lecture 1 part 3 of alternating current. In this we will complete the discussion regarding the AC voltage passing through a resistor, and then we can move forward with a new concept which is called as phasor diagrams. So, I am Sameer Lavankar. This is lecture 1 part 3 of alternating current. Let us begin our discussion. So, currently for the course outline we are working upon this second topic, which is AC voltage applied to a resistor. After this thing is being completed, we can move on to the next concept, which is representation of AC current and voltage by rotating vectors. Okay, fine. So, these thing was completed. Let me try to understand you this example and then we can move forward. Okay, so the example states that a light bulb is rated at 100 watts for a 220 volt supply. First of all, find the resistance of the bulb. Okay. So, basically what is given here? So, basically power is given to you in the question as 100 watts and voltage is given to you. Voltage is given to you as 220 volts. Okay. They are trying to make you understand what is basically the resistance of the bulb. We know that power is nothing but equal to V into I, which is also equal to I square R, which is also equal to V square upon R. So, if we directly link up the last formula, we can directly say that what is resistance? This resistance is nothing but equal to capital V square by P. Okay. So, we can directly relate this, as nothing is given regarding RMS or all that concepts, we can directly implement without using everything except that. So, just put in the value. So, it is nothing but 220 squared upon P, P is basically 100. So, you will finally obtain the value as nothing but equal to 484 ohms. 484 ohms. Okay. So, that is the first answer here. Next thing is find the peak voltage of the source. Okay, quite evident. So, we have understood this concept in the last part also. So, what is this 220 volt basically? This 220 volt is nothing but equal to Vrms. So, this is nothing but Vrms. Okay. So, what is this basically Vrms? Let us suppose this is the sinusoidal waveform. Let us say this is some time t, this is some voltage V. So, actually this is the Vrms value. They are trying to ask you what is this value of Vm. So, we have already understood what is Vrms. Vrms is nothing but equal to Vm by root 2. Hence what we can say that Vm is nothing but equal to root 2 multiplied by Vrms. Hence, we can get the answer as nothing but root 2 multiplied by 200, which is nothing but equal to 311 volts, which is the answer for the peak voltage of the source. The third question says that what is the RMS current through the bulb. Okay. So, RMS current can be directly implemented using this formula only. There is no use of another formula required here. So, what is capital I? Capital I is nothing but equal to P by V. We know the value of P. P is nothing but equal to 100, and what is the value of capital V? Capital V is nothing but equal to 220. Therefore, we can obtain the value of capital I is nothing but equal to 0.450 amperes. Simple mathematics. Finally, we can obtain the value of RMS current as nothing but equal to 0.45 amperes. If let us say I make a new question that calculate the value of peak current. So, how we will calculate the value of peak current? Similar to this case scenario, we will obtain the peak current value of Im is nothing but equal to root 2 multiplied by IRMS, which is nothing but equal to root 2 multiplied by 0.450. This is the answer for your in amperes. This is the answer for your peak current passing through the circuit. Okay. Fine. So, that was a simple question regarding this concept. Try to solve as many questions regarding this, so that you can have a more clear understanding of this complete concept. Okay. So, that thing being said, now let us try to understand this new concept or new part of the topic, which is representation of AC current and voltages by rotating vectors, which is also called as phasors. Okay. So, in the previous section we learnt that the current through a resistor is in phase with the AC voltage. Just to make you understand again what is basically in phase. So, let us suppose, okay, so the diagram is here only. So, if the starting point, if the ending point, or basically if both V and I are 0 at the same point, maximum at the same point and minimum at the same point, then we say that both current and voltage are in phase. Fine. So, that was the first point only. So, in the previous section we learnt about that the current through a resistor is in phase with the AC voltage, but this is not so in the case of an inductor, a capacitor or a combination of these circuit elements. What is its exact value we will get to know in subsequent classes, but for now just understand that the diagram which is obtained here is not the same for your inductor and capacitor. To show phase relationship between voltage and current in an AC circuit, we use the notion of phasors. So, this is how we implement a phasor diagram. The analysis of an AC circuit is facilitated using a phasor diagram. What is a phasor? A phasor is a vector that which rotates about the origin. A phasor is a vector. A phasor is a vector which rotates about the origin, Okay, simple definition is given to you. A phasor is a vector which rotates about the origin. So, this is basically the origin and this is how the rotation is being happening here with angular speed omega as shown in the figure. The vertical components of phasors capital V and capital I represent the sinusoidally varying quantities small v and small I. So, basically with its implementation, how it is performing, we can try to understand how is the phase difference between them. So, if they are aligned properly on each other with the same time, we can say that both are in phase, but if let us say they are moving at different pace or different values, such that at some point at some time t1, let us say example, I am just giving you an example, let us say at some time t1 the diagram for current is in this sequence, but capital V is in this sequence, then we say if this is capital I, this is capital V, then this is a phase difference. This is the phase difference and we basically say that the current and the voltage are out of phase. If they are on the same sequence or they are just aligning one over another, then we say that they are in phase. Okay. So, that is how we can understand this complete concept of phase relationship or phase difference between V and I using the concept of or using the diagram of phasor or phasor diagram. The magnitudes of phasors capital V and capital I represent the amplitudes or the peak values Vm and Im of these oscillating quantities. So, you can see clearly we already know that what is the value of capital I? Capital I or basically is nothing but Vm by R. So, it is a little smaller than that. So, you can see that the length of capital V is a little high on the higher side and the length of capital I is on the lower side. So, basically the length of the vector can also be seen as to denote what is the actual or what we can actually relate physically by viewing that the value of I will be the magnitude value of I will be less than capital V. So, the magnitude of phasors capital V and capital I represent the amplitudes or the peak values Vm and Im of these oscillating quantities. Fine. Next thing is figure A shows the voltage and current phasors and their relationship at time t1 for the case of an AC source connected to a resistor. Okay. So, you can see clearly that this is nothing but phasor diagram. And please remember it is at some time t1. So, basically what would have happened, let us suppose I explain you using, okay. So, let us suppose this is your 4 quadrants are being made here. So, at some time this let us say the what is actually happening, let us say at some time t1 this is the value of capital V and because they are in phase a little smaller value, let us say this is a capital I vector. At some time t2 they may go here, at some time t3 they may go here, at some time t4 they may go here. So, basically and after a complete revolution they will reach at the same, let us say at start my time t is equal to 0 from this location, after a complete this wavy cycle, after a complete this wavy cycle is complete or one complete sinusoidal waveform is complete, this waveform or this wave will complete its complete circle and then reach at the same position. In another sequence I will try to explain using this diagram what is actually happening. So, let us say that this is the sequence being explained for this point. Okay. So, how is this is being explained here? At some time t1 just drop a perpendicular to this location and then move it towards left. Okay. If I make a circle like this, So basically this is at some time t1. Let's say I say at some time t2. So for example, let's say the another time t2 will be this, or let's say this is at some time t2. Okay, so again drop a perpendicular like this, go towards left, and then you can obtain. So the circle is exactly not, some sort of this can be obtained. So that is how we can obtain this value. So after this complete cycle is obtained, so at this location, so from start, let's say I say t is equal to 0 and t is equal to t, that is complete time, you can obtain that this complete circle diagram is being created. So that's how a phasor diagram actually works. So just explaining how to make this phasor diagram. Let's say you need the answer at some time t1, just drop a perpendicular, and then on this circle, the virtual circle, just try to pinpoint at that location, and that is the location of the vector of the phasor diagram at that time t is equal to t1. Okay. So figure A shows the voltage and the current phases and the relationship at time t1 for the case of an AC source connected to a resistor. Please remember, this is only for the case of an AC source which is connected to a resistor. For a case of inductor or capacitor or the combination of all of them, this sequence may differ. Okay. The next thing is the projection of voltage and current phasors on vertical axis, that is Vm sin omega t and Im sin omega t respectively represent the value of voltage and current at that instant. So basically what they are trying to say, I will try to explain again with another diagram. They are basically saying is, let us say that at some time t1, this is the vector capital V. Okay. If I try to, so this is nothing but what? This is nothing but omega t1. So this value, this vertical value is nothing but equal to, this particular value is nothing but equal to capital Vm, sorry, small vm, not capital Vm, it is Vm sin omega t. Okay. That is the concept which is they are trying to explain here. So this length is nothing but equal to Vm sin omega t. So if we need to calculate the value using a phasor diagram, we can just find out the vertical component of that vector and then we can obtain the value of current. Also current or basically voltage depending upon the vector which we are using. Okay. So the projection of voltage and current phasors on vertical axis, that is Vm sin omega t and Im sin omega t respectively represent what? They represent the voltage and the current at that instant. Please remember, this is the AC voltage and AC current which we are talking about, correct? Okay, fine. Moving forward, so in this complete representation of AC current concept, there is no use of RMS value or nothing else. That thing is done for now. We are just trying to understand everything in terms of your AC voltage and AC current only. So as they rotate with frequency omega, curves in figure B are generated, as you can see. So this is basically, so how this is being generated. So you can either go from left to right, you can either go from right to left also. So let us say at some time omega t1, this is the point, we will just go in this sequence here. At some time t1, we will drop a perpendicular from this location and we will drop a horizontal line from this location. The point at which it will meet is the location of the virtual voltage value at some time t1. Okay. So from figure A, we see that the phasors V and I for the case of a resistor are in the same direction. So you can see they are in the same direction. This is so for all time. So basically at some time t2 also they may go like this and like this, at some time t3 they may go like this and like this, t4 they may go like this and like this, but they will be always in the same direction. This means that the phase angle between the voltage and the current is 0. So the concept which I try to explain here, okay, I removed that diagram. So let us suppose that if for some another device, this is your capital I and this is your capital V, then the angle between them is nothing but called as your phase angle. But because both of them are aligned in this sequence, therefore this time the value of phase angle between them will be 0. Okay. So that was the only concept regarding your phasor diagrams. Now let us try to understand new discussion, that is AC voltage applied to an inductor. The concept of inductor was already been explained in subsequent previous chapters. So I won't go into what is an inductor. We will try to understand what happens when AC voltage is applied to an inductor. Okay. So similar case scenario as in the case of resistors, a simple circuit is being explained here, an EMF with an alternating current. So basically this type of diagram is being shown here, and in case of only differing part is that in the previous case there was a single resistor which was being implemented there, this time a single inductor is being implemented here. The only difference is that so for ideal case scenario we are assuming that the internal resistances in all these wires is 0. Okay. So, now just try to everything is now mathematical input, just try to understand this. So, figure shows an AC circuit connected to an inductor already shown. Usually inductors have appreciable resistance in their windings, they have some resistances here, but we shall assume that this inductor has negligible resistance. So, there is no resistance in this circuit here. Thus, the circuit is a purely inductive AC circuit, quite evident, there is nothing else, only induction is being explained here or being worked upon here, and we have only an inductor in this complete AC circuit. Let the voltage across the source be V is equal to Vm sin omega t. Similar as we started with the previous discussion regarding resistor, we started with V is equal to Vm sin omega t, and we are trying to calculate the value of what is value of I in the circuit. So, using Kirchhoff's loop rule, summation epsilon of t with a function of t is equal to 0, and since there is no resistor in the circuit. So, this is basically how we say that what is the complete voltage, voltage will be nothing but equal to L di by dt. So, I think you remember this formula for the voltage across a inductor, that is nothing but L di by dt. What is L here? L is the inductance of the inductor. Okay. Where the second term is the self induced Faraday EMF in the inductor and capital L is the self inductance of the inductor. So, we also understood the concepts of self inductance and mutual inductance. I will not go into detailing, those things have already been explained in subsequent previous chapters. We must just remember that what is capital L here, capital L is self inductance of the inductor. Okay. Negative sign, why it is a negative sign? Because negative sign follows from the Lenz law. Okay. So, that thing being said, now let us try to derive this relation here. Okay. So, first of all we have small v is nothing but equal to capital L di by dt. Okay. Now, we know that what is di by dt? So, di by dt is nothing but equal to capital V by L. What is V here? V we know that is nothing but Vm sin omega t divided by L. Okay. So, this is the simple, nothing is explained here, just I defined V is equal to Vm sin omega t. Now, what we need? We just need the value of I. Okay. How to get the value of I? If we just integrate the value of di with time, we can obtain its value. So, just integrating both sides. So, let me just write. So, to obtain current, we integrate di by dt with respect to time, Okay. So, integrating both sides, what we get? Integrating di by dt is equal to integrating Vm by L sin omega t dt. So, it is integration of di which is equal to Vm by capital L integral sin omega t dt. So, basically I is nothing but equal to Vm by omega L cos omega t dt, cos omega t plus some constant. Okay. So, that was the final relation being obtained. Let me stop it here only. I will try to explain you what will be the constant factor here. I will try to explain what is the basic use of this cos omega t in the subsequent lecture. So, let me stop it here only. In this discussion we have started with the discussion regarding is representation of AC circuits, basically phasor diagrams was being explained, and then we understood the new concept, that is AC voltage applied to an inductor. After this is being done, we will move on to capacitor, and then we can finally try to combine all of them in a series LCR circuit. Then regarding concepts such as resonance etc. will be understood, but the final crux of this data was, first of all we understood basically what happens in a phasor diagram, and then we try to understand next lecture that what is the basic significance of this cos omega t being occurred here. So, that thing being said, let me stop the discussion here only. Thank you so much.